Rn has infinitely many bases. The only thing common between these bases is that they have to have the same number of vectors. So for an n-dimensional space, it has to have n basis vectors. As a general rule, we use the most convenient basis for whatever problem we're working in. Now, generally, standard basis is our most convenient one, but right now we're going to consider a different basis. This one is dependent on the matrix you have in your problem. Some matrices have a built-in preferred basis. In this basis, a matrix acts very similar to a diagonal matrix. Now, to try to make all of this very precise, I want to go through an example with you here. Here is a matrix. Now I'm going to give you these two vectors out of the blue. Didn't tell you where they come from. We won't worry about that right now. There's a nice observation, and it's geometric. I'm going to consider what happens when this matrix acts on each of these vectors. Remember, we've been studying matrices as transformations, so what we want to study is how this matrix transforms each of these vectors. This first vector ends up giving you this result. Nothing happens to the vector. In the second case, when that matrix multiplies this vector, all it does is becomes stretched. It's very simple. That is going to be very useful for us. This observation forms the basis for a definition that we are going to use throughout this chapter, something called an eigenvector and an eigenvalue. So we're going to denote an eigenvector by v and an eigenvalue by lambda. An eigenvalue, lambda, is a value such that when you take your matrix A and multiply it on your vector v, it just scales it. It stretches or compresses it. And the only thing that we're going to require is that that vector is non-zero. And that's called our eigenvector. Now I'm going to abbreviate eigenvalue and eigenvector just by E because I'm lazy. An eigenvalue and an eigenvector are a pair. There's always an eigenvalue associated with an eigenvector. So this is the key idea. Matrix multiplication, all it does is ends up just stretching your vector in the same direction the vector was in. Now back to that example that we talked about. If I give you the same matrix again, now I'm going to consider some vector x. If I were to multiply this ax, it's going to do something to that vector. What did it do? What geometric effect did A have on this vector x? This matrix has hidden within it some preferred directions. You can't really see that by looking at the matrix on its own. We're going to introduce the idea of an eigenvector basis for R2. The V1 and the V2 that I gave you earlier. 1 and -1, 1 and 1. These two vectors are independent. They are not multiples of each other. If I put them into a matrix, that means there'll be a pivot in every column. Since these vectors live in R2, that means there'll be a pivot in every row of that matrix. Hence, they are a basis. If it's an eigenvector basis, any vector can be written in terms of those basis vectors. To do that, I have to solve the system V1, V2 augmented by x. So it's a simple row reduction. Now you can go ahead and do the row reduction. It's pretty quick. What you're going to end up with is 1, 0, 0, 1, -3/2, and a 1/2. So that tells you how your vector is represented in this eigenvector basis. -1, 2 is the standard basis representation. This is the eigenvector basis representation of x. Why do we care? Why is this important? I'm going to try to illustrate it to you with a picture. We've got our vector -1 and 2. I need to go over one unit to the left and up 2. So there is the vector x, and its image turned out to be 1 and 4. So the image of that vector ended up being over here. Now you might say, well, what is this? Is this some kind of stretch, a rotation? We want to look at it from the point of view of an eigenvector basis. And this is a property now that we have been using over and over and over again in this course. When we take a matrix multiplied by a vector, there is the linearity property. All of this stuff here is based on exploiting that. Now, if V1 and V2 were just some regular vectors, this wouldn't be helpful for us at all. But they aren't just regular vectors. These are eigenvectors. When you do this multiplication from earlier, we learned A times V1 is just V1, and A times V2 gives you 5 bunches of V2. So the matrix multiplication stretches our vectors in these preferred directions. So what does that mean? On our picture here, I can easily draw V1 and V2. They form their own coordinate grids. They all go along these diagonals here. I can use this idea to figure out what my original vector looked like in terms of eigenvector basis and what my image looks like in terms of eigenvector basis. The original vector x was -3/2 bunches of V1. So there's -3/2 V1. And it was a half bunch of V2. So it was right there. And that means I draw a parallelogram. The vector x, the original vector, is right there, and it satisfies the parallelogram addition rule. The new vector, the image, is 5/2. The V1 doesn't change, but the V2 component does change. It goes all the way up to 5. Sorry, not 5/2. 5/2, that's where I want to go. And if I were to draw this parallelogram here, you can see, oh, there I am. This is why we want to exploit eigenvector basis. We had to kind of turn our head and look at it the right way. So the action of A was to leave the V1 component alone and stretch the V2 component by a factor of 5. And that's what happened to this blue vector here. Its V2 component was there originally. It got stretched by a factor of 5. So this vector essentially just got stretched in one direction. Nothing else happened. And that means A acts like a diagonal matrix on the V1 and V2. And it kind of acts similarly, and I'm going to put that in quotes as not precise, to some diagonal matrix 1, 0, 0, 5, where you could imagine that the 1 is acting on the V1 component and the 5 is acting on the V2 component. We're going through all of this trouble because if you put yourself in the right basis, it makes life really, really easy.